Okay, so s orbitals, one s orbital on each principal energy level, and they're the lowest. So in the hotel, the s room is always cheaper than the p room or the d room on the same floor. And then once you get above n equals 1, each of those energy levels is going to have p orbitals. And there will be 3 p orbitals because of the quantum numbers. And these p orbitals are aligned along the x, y, and z axes. If you remember back to graphing in three-dimensional space. The p orbitals have 2 lobes, and they each have one node at the nucleus, and then the larger ones are going to have a total of n nodes. So if n is 3, they're going to have a total of 3 nodes. So this is what the p orbitals are shaped like. So this is the kind of like the time-lapse or multiple exposure version, and here is enclosing, I think it's a 90% probability. So there's one along the x-axis, one along the y-axis, one along the z-axis. And there's a node at the nucleus. So the 2p orbital has 2 minus 1 lobes. It has 1 lobe, and that's at the nucleus. And if we look at that radial probability graph, we see that there's 0 probability of the electron being at the nucleus, and it rises out here and then falls down again. And so the electron is occupying both lobes, but it's not at the nucleus. And again, the idea of the standing wave helps with this, because we can think of this as a standing wave, and there's a node at the nucleus. Okay? I think of the shape of these as being a little bit like 2 balloons tied together with a gap there. Then the d orbitals, there's more of those, there's 5. N equals 2 doesn't have any, but n equals 3 has d orbitals. And these are designated, there's dxy, dxz, dyz, and dx squared minus y squared. So these are different planes in the three-dimensional space. And then there's, the 5th one is along the z-axis. Most of these are 4-lobed, but the one of them is a 2-lobed toroid. Nice. Yeah, right? I'm sorry. I'm sorry. So you thought the p orbitals were weird. These are even weirder. So here, this is one orbital. This is another one. It's the same shape as this one, but it's horizontal. This one's vertical. This one's vertical in the other direction. And then this one's horizontal, but it's not lined up on top of this one. It's lined up so that these, that its lobes are between the lobes of that one. And then this guy's just freaking weird.
So one of those represents 1 electron.
Each represents 1 orbital. And they can each have 2 electrons. Mm-hmm. Yes?
Do you even know all 5 of these orbitals, or is this just information?
This is more for your information. I want you to have a clue about the shape. I will not make you draw these on an exam. I won't. Yes?
So those orbitals, do they like overlap, or how does that work?
They don't overlap very much.
Or like contain one inside the other?
You mean the P and the Ds?
Yeah, because...
The P's and the Ds do overlap.
Okay.
But the d orbitals do not really overlap with each other much.
You're not going to see all of them at once.
Well, if you had electrons in all of them, they'd all be there, yeah. And these are, you know, I really like my hotel analogy. Even if there aren't electrons in these d orbitals, the d orbitals are possibilities for the electron. If it gets the right amount of energy, it can get into this standing wave. And these are harder to picture as a standing wave because we can't make that with a piece of string. But it's the same idea. And so these would be 3D orbitals, and then if you go to 4D, then they start getting spherical nodes within those lobes. things, they get more and more complicated. Then there's the F orbitals. These are really trippy. There's 7 of those. Right? Looks like the balloon artist went crazy. I couldn't draw those. I would never ask you to draw those. But there you go. You've seen them. There they are. And, we did not make this stuff up, right? We're using experimental observations, and they've come up with this mathematical description with these different quantum numbers, and when you plug in the different quantum numbers, these are the shapes that get generated. It's math's fault. Okay, so orbitals are determined from mathematical wave functions. And the wave function can have a positive value or a negative value. It can also have nodes, and in the node, the wave function is 0. So the sign of the wave function is called the phase. And so just like waves in the water or the waves on that piece of string, these waves can interact with each other, and they can interfere constructively or destructively. So when orbitals interact, and this is going to be the orbitals of one atom interacting with orbitals of another atom, they can be in phase or out of phase. And we'll be looking at this later when we talk about bonding. So here we have the 1s orbital. And this would be like the string with just the one standing wave, that a node at each end, but no nodes in the middle. And so it can either be up or down. And then a p orbital is going to have a full wavelength here, if we use the string analogy. And so this side is up and this side is down. And we just use red and blue. So red and blue are different phases. So we've got all of these weird shapes, right? And yet we think of atoms as being spherical. Well, we depict them as spherical because if we take all of those orbitals and superimpose them on each other, good luck drawing that, the shape is roughly spherical.